I am Aurel Page, and I will lecture on computational computational mathematics focused on number theory. And so today's lecture will be about a few generic algorithmic techniques and then L functions. So I will start again by a reminder of the previous lectures. So remember the first lecture, we talked about complexity. So complexity is the expression of the running time of an algorithm as a function of the size of input. And I gave 4 complexity classes to give a rough classification. Fast algorithms, quasi-linear, medium, polynomial time, but not quasi-linear, slow, sub-exponential, but not polynomial, and very slow exponential algorithms. Then we talked about the complexity of basic arithmetic operations. We saw that basic operations on integers and polynomials were fast, quasi-linear. Basic operations on matrices and factorization of polynomials could be done in polynomial time. And factorization of integers, that is a hard problem, that's slow. During the second lecture, first we talked about reconstruction algorithms, which allow you to recover an object from specializations or approximations. And there are fast algorithms for reconstruction. So they can be of various types. You can reconstruct integers from modular or multimodular approximations or real approximations, polynomials from evaluation and interpolation, rationals from continued fractions from a real approximation, and rational fractions from pade approximants. Then we talked about various problems in algebraic number theory. First, the computation of the ring of integers, which has 2 steps. The factorization of a discriminant, which is difficult, possibly. And then the computation of p maximal orders for various p, which can be done in polynomial time. We talked about ideal factorization. So this starts by an integer factorization, again that is slow, and then prime decomposition and valuations, which can be done in polynomial time. Then we talked about computation of Galois groups in 2 settings. Either the input field is already Galois, or we are starting with a small field and we are trying to compute the Galois group of the Galois closure of that, without actually computing the Galois closure. And we talked about computations of class groups and units. And for this, there are sub-exponential algorithms under the GRH and exponential algorithms unconditionally. In the third lecture, last lecture, we talked about linear algebra. So assuming that we have a faster matrix multiplication than the naive one, which would be n to the omega with omega equals 3, and we saw that you can lower that a bit. So in this case, you can do linear algebra operations like solving systems, computing image, kernel, etc. in essentially the same time complexity as matrix multiplication. However, that's only counting ring operations, and over infinite rings, you can have a problem with growth of coefficients. And so just applying these algorithms can lead to exponential time algorithms. So you have to use other techniques, and in fact you can obtain polynomial time algorithms based on reconstruction. But the complexity will be higher according to the size of coefficients involved. And then we had a few methods with examples on how to reduce a problem to a linear algebra problem. And we talked about logarithms, Newton's method, and index calculus methods, in which the central concept is that of a factor base over which we try to factor elements. Okay, and finally, in last lecture, we talked about lattices. So reminder, a lattice is a subgroup of a real vector space that is generated over Z by an R basis. And we had a few lattice problems that we examined. The shortest vector problem and its approximate version, the closest vector problem and its approximations, and the isomorphism and automorphism problem. We saw that you could have a time approximation trade-off for SVP by having an extra parameter, a block size. And not only these type of algorithms were solving approximate SVP, but also giving a notion of reduced basis, a basis with shorter elements and somewhat orthogonal. We had some useful but very slow algorithms for lattice isomorphism. And we talked a bit about how to identify a lattice problem in general. Either you could have a notion of reducing the size of an object when you allow certain linear transformations, or you could have a problem that is visibly linear, or I mean, in the sense of linear algebra that we saw before, but with additional size constraints in your problem. Okay, so that was for the first 3 lectures, and today we're going to see some general algorithmic techniques that can be used in a variety of contexts. So these are taken from algorithms a bit outside of mathematics and number theory, but that can be applied to the problems of interest in algebra and number theory. And then L functions, so this is a bit of a more mathematical maybe part. So L functions is a very important concept in number theory. I think it's important that you have seen it. And we will see algorithms related to L functions and applications of L functions to algorithms. Okay, so let's start with general algorithmic techniques. So very basic but useful technique is that of sorting. So if you have an array of objects that are not necessarily in increasing order, you can sort them in O of n log n time, where n is the number of objects. So that's fast, quasi-linear. There are several types of applications, but I will focus on 2 main ones. Either you have this array and some of the objects in there are actually isomorphic, I mean identical or isomorphic, and you want to remove the duplicates. And so so the focus really is on the resulting list when you've removed the duplicates in this case. And another type of application is you have this list of objects and you want to find a pair of objects in this list that are actually the same. That's what we call a collision. So here the focus is really you're interested not in the rest of the list, that's kind of garbage. What you're really interested in is the collision, the ones that are the same. Okay, and so both of these can be done by sorting. So let's see some examples of these 2 types of applications. So, okay, the problem of removing duplicate objects. So I will express it in a somewhat generic form, and then we'll see an even more concrete example. So you imagine that you have n objects in your array, and you want to remove the duplicates. So imagine that you just have an isomorphism test for this type of objects. Then you have to do all the pairwise isomorphism tests to be able to remove the duplicates. And that takes quadratic time, right? You have to try every pair of elements. So that's a bit inefficient. But if you want to do better, you have to you have to have something stronger than just being able to test isomorphisms. You have to have either a canonical form. So a canonical form is a way of representing your object that only depends on its isomorphism class. So whenever, if you put the objects in canonical form and they are isomorphic, they will be literally equal in this representation. An alternative to that is if you have complete invariants. A set of invariants, maybe like numbers or data of another type that completely characterize the object up to isomorphism, even if you don't change the representation of the original object at the same time, you can just test isomorphism by directly comparing the invariants. So if you have one of these 2, you can put in your list, your array that you sort, this canonical form or the complete invariance. So you have one computation of such things to do for each element, so that's an O of n computation. And then you do the sorting, and once the elements are sorted, you identify the identical ones in this case, and you remove the duplicates. So sometimes it's difficult to obtain something as strong as this, canonical form or simple complete invariance. So you can apply a slightly weaker form of this. So for instance, you could have what I would call a pseudo-canonical form, meaning so usually objects have an infinite number of possible ways of representing them. But you might be able to turn an arbitrary representation into a small one for which such that there's only a small number of possible representations for a given isomorphism class. So if you turn objects to a pseudo-canonical form and you remove the duplicates, you will not have necessarily removed all duplicates, but usually it will reduce greatly the number of duplicates. So that gives you a partial solution. And another way to do things is to have a set of invariants that not necessarily completely characterize isomorphism, but give you enough information that there will be very few non-isomorphic sets of elements that have the same invariants. We'll see an example in a bit. And so if you have this, you only use these invariants when sorting. You group the object after the sort. You can group the objects that have the same invariants. You'll have blocks, groups of elements that have the same invariants but are not necessarily isomorphic. And then you pairwise test for isomorphism only inside the groups, and that's quadratic, but only in each of the small groups. So depending on how small you can make these groups, this can also be fast. Okay, so let's see a more concrete example that actually comes from algebraic number theory. So the problem is the following. We'll fix a degree, and we would like to find all number fields up to isomorphism of degree d such that the discriminant satisfies a certain given bound. So by a theorem of Hermite-Minkowski, this set is actually finite, so it's a well-defined problem. And you can make this theorem actually explicit in the following form. This is Hunter's theorem, and the diagram we'll describe is called Hunter's method or Hunter search. So every number field of degree d with discriminant that is below a certain bound admits a defining polynomial such that the coefficients are bounded as a function of x. There's a different bound for each coefficient, but the bound depends only on x. And this leads to the following algorithm. You enumerate all the polynomials that satisfy these bounds. So that will be a huge set of polynomials usually. Then you keep only the ones that have discriminant below the bound, because actually, these bounds are not their necessary conditions for the discriminant bounds, but not sufficient. Usually, a polynomial within these bounds can have much higher discriminant. So you keep only those. And then you want to remove the duplicates between the resulting list to have just one representative for every isomorphism class. And so, okay, there is a way to obtain a completely canonical form for number fields, but I think it's more interesting to talk about the slightly weaker version, because also it applies even in larger degree. So you have a pseudo-canonical form given by the reduced defining polynomials. Remember, we said that using lattice algorithms, we can replace the defining polynomial of a number field by a smaller one. And in fact, if you look at this construction a little bit, you'll see that there are very few possible defining polynomials for a given number field using this method. So that allows you to remove many of the duplicates. And then you can use a set of invariants such as the discriminant of the number field, the signature, meaning the number of real embeddings and or of pairs of complex embeddings, and the decomposition type of small primes, that is the number of primes below a certain prime number of Q and their inertial degree, residue degree, this kind of data. So all of these are isomorphism invariant, of course, they only depend on the field up to isomorphism, but they don't completely characterize isomorphism. In fact, you can even have pairs of non-isomorphic fields that have the same decomposition at all primes, like not just a small finite set of primes, but all primes. So you'll never get complete invariance like this. However, this is enough to reduce to a very small number the possible candidates for duplicates. And so once you sort your huge list according to these invariants, you only have very few actual isomorphism tests to end up with just a list of isomorphism classes. If you add up the total complexity of this, well, of course, to analyze this, you have to know what the exact bounds are here. I'm not showing it for simplicity. The total complexity is x, the discriminant bound, to the d plus 1 over 4, where the constant here is actually allowed to depend on the degree of the field. Okay. So this can be used for degree up to 9, where this is actually possible to do. Yeah, just one thing I wanted to mention here is what the number of fields that you actually expect in the output here should be big O of x. So only linear in x. That's actually a conjecture that is known only in very small degree. And in general, the best bound we have is x to the log square of the degree. I mean, a constant times log square of the degree. So we don't really actually know what the size of the output here is, except conjecturally. Okay, another application of so this was an application of the type remove duplicates. Now we are going to see an application of the type find collisions. Okay, so the problem is the discrete logarithm problem, which we've already encountered, and we saw how to solve it efficiently, I mean somewhat efficiently, in the multiplicative group of finite fields using index calculus. Here we are thinking of this problem as being in an abstract group where we don't know any other special properties. So recall the problem. We have a cyclic group G with a generator G that is given, and we are given another element H. Since G is a generator, H is a power of G, and we want to find the power. So the naive algorithm to do that would be to just try every power of K and compare the elements. So the time complexity of that would be O of n, the size of the group. Just try every power. Okay. So using the method I will describe here, which is called baby step, giant step, you can reduce that to essentially square root of n. Okay, so how does this work? Well, we are going to look for the discrete log k as a plus bm, where m is essentially the square root of n. Okay, so we write this discrete log in base m. It will have just two coefficients, which are both essentially of size square root m. Okay, so how do we proceed? We compute the set of all powers of G up to m minus 1. That's what we call the baby steps. So, well, how long does it take? You just compute each element from the previous one by multiplying by G. So this is just O of square root n multiplication in the group. And then you compute what we call the giant steps, meaning h times G to the minus m, h, etc., multiplied by G to the minus m every time. So to compute this, you first raise g to the power minus m once, and then you start with h and you divide, and you multiply by g to the minus n every time to get the next one. So this takes also only O of square root n steps. Okay, multiplications in the group. And once we have these two lists, we can sort them by doing this sorting, find collisions between the two lists, right? Where once you have the two sorted lists, you can traverse the two lists in parallel, like going forward in the list that has the smallest element, so that you can find a collision between the two. And once you have a collision, well, it will be an expression of the form g to the a equals h times g to the bm, and that exactly gives you the discrete log of h. And you know that you will find a collision because the discrete log can be written in this form, and therefore there has to be such an inequality. Okay? And if you put everything together, the complexity is essentially square root of n. So this is still exponential time, but it's much better than n, the naive algorithm. Okay, so that's a collision type application of sorting. Okay, I just want to mention a few other general programming techniques without any details, just to let you know that some things exist, and then you can, if you realize that it could be useful in one of your applications, you can look them up in more details. So that's various kinds of data structures. So what's a data structure? It's an object that contains a certain number of elements, I will call it n here, and that supports certain types of operations. So there's a wide variety of data structures, and depending on what you do, you'll use some of them, or you will design one for maybe your specific problem. So, okay, as a very basic example, just for comparison with the other ones, an array is just, so it is a type of data structure that you can create with a certain fixed length, and you can access an arbitrary element, modify it or read it in time O of 1. So you can quickly read or modify an element, but not extend it, for instance. So if you don't know the number of elements that you'll have in the end, it might be better to use something slightly different called a chain list, where each element knows basically its neighboring elements. In this case, you don't have fast access anywhere in the middle of the list, but you can append an element at the end, or in fact in the middle, or read the next element when you are reading somewhere in time O of 1. So this is usually useful when you don't know the length of whatever set of things you're going to compute, and you want to be able to quickly extend it without doing a full copy. Okay, more interesting are, so for instance, balanced trees, which are usually called set or something in programming languages. And these support, they're allowed to represent a set of elements that you can insert quickly. You can find quickly if some element is already in there, and you can also quickly delete an element. So that's the kind of queries that it can support. A few other examples. So the priority queue, that's sometimes useful. So it supports fast insertion and deletion of an element, but the main operation is you're able to quickly extract the maximum element that is stored in the data structure. And just to give you elements of things a bit more varied that you can have, so there's something called interval trees, which allow you to store a certain set of numbers, or objects that you can compare, in fact. And you can insert and delete quickly, but the interesting operation is that you can make a query for an interval and it will quickly find the number of elements in this interval without going through the full list of elements, right? It contains n elements, so the naive way of doing this would be to go through the whole list and count how many elements are in the interval. But this data structure can do that quickly. And there's a wider variety of other things. And if you realize that maybe one of your problems could be solved by a data structure supporting certain queries, then you go to your computer science friends and you ask them for, does there exist a data structure that does what you want? Okay, so now I will describe a number of applications of graphs. So graphs usually belong to discrete mathematics or general mathematics, but they can be a useful way of thinking of certain problems also in algebra or number theory. So what is a graph? It's just a set, a pair VE, where E is a set of vertices, which we usually represent as points. So that's V. And then a number of edges that connect the pairs of their vertices, like this. And there are variants. You can give a direction to the edges or not. You can allow multiple edges. You can add a label on the edges, for instance, numbers like this. All of these variants encode a certain information in a different way. And a morphism of graphs is just a map between the vertices that preserves the edges, sends edges to edges. If you have weights, they must be preserved, etc. And so why is it useful to think in terms of graphs? Well, it encodes your information in a more abstract way, so it can be a way of forgetting about what doesn't actually matter for your problem and then think a bit more visually about it. So let's see some examples. So an example of application where thinking in terms of graphs is often useful is sparse linear algebra. So what is sparse linear algebra? Well, it's operation on sparse matrices. A sparse matrix is a matrix that has a lot of zeros, like mostly zeros, and therefore you only want to store the non-zero elements, and when you do operations on them, you want to preserve this sparsity property. So it's typically a good idea to think in terms of graphs when you manipulate sparse matrices. So let's see a simple application on index calculus algorithms. So remember what happened in index calculus. You had this set of primes, and you were drawing random elements, hoping that they factor over this factor base, this set of primes. And then in the end, you end up doing linear algebra on the matrix obtained from these factorizations, from the relation matrix. So the more primes you put in your factor base, the more likely it is that you will find a relation. So you would like to increase the size of the factor base, but then your linear algebra is more costly. So one thing that is useful is to allow a bit more primes than you would usually take, but you restrict to having a very small number of occurrences of these extra primes, allowing for operations that don't require the full linear algebra algorithms, but dedicated algorithms to simplify this part of the matrix. So that's called the large prime variation in index calculus. So for instance, you add these large primes after your factor base, but you only allow relations that have, for instance, one large prime or two large primes. Okay? So how does it work? Well, if you allow only one large prime, that will mean that you have in your relation matrix, so in the large prime part, you'll have relations with exactly one non-zero entry. Then there's a lot of things in this part, in the small primes part. And when are you able to eliminate these coefficients? When that's exactly when you have a collision between the large primes. So like these two, if you have a non-zero key in these two, you can do a suitable linear combination of these two relations, get rid of one of them, and then you have no large prime left for these two rows. Okay, and so you can eliminate a bunch like this. So this is an instance of collision finding. So as we saw, you can do that by sorting this part, and you find collisions this way. So the two large prime variation, let's say that we're doing linear algebra mod 2 to simplify. You will allow two non-zero coefficients. So something here on the left, and in each row you allow two non-zero coefficients. So, well, okay, maybe I want some a bit more. Yes. So a good way of thinking about this is by forming the following graph. You will have one vertex for each large prime, and each relation that has these two primes appearing will be represented as an edge. Okay, so I will give them numbers maybe here, or letters, A, B, C, D. So for my example here, and so, okay, the first relation has A and D, so we'll put an edge here, then A and C here, B and D there, and C and D here. And with this point of view, what you are looking for is a cycle in the graph, meaning a path of edges that goes back to the first element. And why is that what you want? Well, when you have such a cycle, like, so here this one is the one you're looking for, you can sum the relations corresponding to this cycle, and it will exactly eliminate all the large primes. So like this one, so these two, so which ones? So these two will cancel out, these two will cancel out, and these two will cancel out. So the sum of these is a relation that doesn't involve any large primes. And yeah, so it's useful to think in terms of this cycle. There are efficient ways of finding cycles in graphs. Okay, let's see another example coming from sparse linear algebra. So now you have a sparse matrix, so full matrix, I mean in abstract context, you don't have to know where the matrix comes from. And when you store a sparse matrix, you don't want to store every coefficient. You will only store the list of non-zero coefficients. That's enough information. So you list pairs of indices and the corresponding non-zero coefficient of the matrix. And the graph way of thinking about this is as follows. So you have your so your matrix has n columns and m rows, and you will think of the columns as being left vertices. So there are n of these and m of those. And these essentially represent the basis of the domain space. This is the basis of the codomain space. And non-zero coefficients will be arrows between one side and the other. So like when you have a non-zero coefficient, it will correspond to one of these edges. Okay? So you obtain what we call a bipartite graph, meaning a graph with which is divided into two sets of edges, but in which, of vertices, but the edges must connect one side to the other. There cannot be any edges on one side or on the other side. Okay. So that's a more visual way of thinking about it. And now you can reinterpret Gaussian elimination in these graph terms. You can forget about the actual algebra once you do this. So I won't give all the details here, but a set of pivots that you can use to eliminate rows and columns in your matrix correspond to what we call a matching in the graph. So matching means selecting a set of edges that have no common vertex. You're not allowed to select two edges that have a vertex in common, and you need an extra condition to make the actual linear algebra work. And then you can prove that this graph interpretation allows you to eliminate rows and columns in your matrix. And it can be hard to find actual optimal matching, but thinking in terms of this graph and having this visual interpretation allows you to have good heuristics that are good enough to actually have very fast sparse linear algebra. Okay, I'll do one more example and then we'll take a break. So the next example is a little bit in the same spirit, but in sort of one more dimension way. So one extra layer that you can put on linear algebra is what we call a homological algebra. So the basic object is a complex of vector spaces or groups or R modules. So a complex is a sequence of vector spaces, let's say, with maps between them from one to the next, and satisfying the important property that if you apply two successive maps, you get the zero map. And that's the important property. And so in particular, that's the same as saying that the image of one map is contained in the kernel of the next map. Okay, that's the same. And the important object in this context are the homology group of this complex, meaning you have this image contained in the kernel and you take the quotient of the two. Okay? This may be slightly abstract, but let me give you, a simple example to see that you recover familiar objects. If you simply have a single map, a single linear map, you can form the following complex. You just put a 0 at the beginning and at the end, and then computing the homology group is the same as saying you want to compute the kernel and the co-kernel of the map. Okay? But more generally, there are many contexts in which this construction is actually the object of interest. So you get long complex with several terms, and these are the objects of interest. You're not actually interested in keeping the kernel itself or the image itself, but just these homology groups. So this also has a graph interpretation when all of these maps are sparse. You just do the same construction, except that you'll repeat it with extra layers. You'll have an extra layer, and you can have as many as you have vector spaces in your chain. And using this interpretation, there is something that is of topological interpretation that allows you to do some kind of elimination. It's called algebraic Morse theory, and it uses some zigzag paths. So maybe I'll just show you an example to see just what it looks like. It means paths that go from one side to the other and then the other direction, and then like this, something like that. Satisfying some extra conditions as before, and if you can find a zigzag paths where all the weights are invertible, where the weights are the coefficients that were actually originally in the matrix, then using this, a type of counting of this type of paths, you can transform your whole complex into an equivalent one that has the same homology. So the same homology groups, which were the things you were interested in. So this is slightly more powerful than elimination in the sense that you don't just do invertible operations on your matrices. You're allowing something more brutal than that preserves the homology, but not necessarily, for instance, the kernel itself or the image itself. So because you're allowing a transformation that is more brutal, then you can hope to have a more efficient simplification. Okay, I think this is a good time to take a break. Okay, let's see another application of graph interpretation of a problem. So this has nothing to do with linear algebra. So the goal here is to encode a certain equivalence relation on a set of elements. So you have a set of elements, and you want to be able to declare a certain number of elements to be equivalent, and compute with the equivalence relation generated by this. Okay, so one way to think about an equivalence relation is to think of your set as being the set of vertices of a graph, and then when two elements are declared equivalent, you think of an edge between the two, and then what are the equivalence classes? They are exactly the connected components of the graph. Okay, so that's the geometric way to think about it. And so there's an algorithm called, its name is union find, that allows you to quickly add the relation between two elements of your set, or quickly find the representative of a class of elements. Like as the algorithm proceeds, each equivalence class has a unique representative, and you want to be able to find it to compare if two elements are equivalent or not. So how does it work? So you start, instead of pointing randomly, when you add the relation, you will put an oriented edge like this, pointing, well, not just to the next elements, but to the representative of the class. And then, okay, you add another relation. And sometimes you want to add a relation between elements that are already in some equivalence class. And in this case, what you do is you decide on a single representative for the whole class. So for instance, when you want to add one between these two, you don't add an edge like this, because this one already has a representative, which is this one. You directly add an edge like that. Okay. And now let's say that we want, okay, maybe I need a few more elements. Okay, let's say that I want to merge also these two, so maybe I will add something like this. And now let's say that I want to merge these two. In this case, I will first compute the representative of that element by following the arrows, and I end up on this one. But as I do that, instead of keeping these relations as they are, I will merge everything, but I will also update this one to point here. And the effect of this is that the length of the path that you have at any point is always very short. And you can analyze this precisely. So there are basic analyses of this that give you O of alpha of n, where alpha is just like the iterated logarithm, like the number of times you have to apply log to be below 1. And even more refined analysis give you the inverse of the Ackermann function. So this is a hugely fast growing function. So alpha of n, the inverse, is hugely slowly growing. So in practice, this is the height is bounded by like 3 or 4 always. So this is a fast way of representing an equivalence relation, and when you can add, declare elements to be equivalent. Okay, so now let's talk about the graph isomorphism problem. So, I mean, whenever we have a type of object that we consider, we have the isomorphism problem that appears. So the problem is we have two graphs and we want to find an isomorphism between them, or a variant, of course, is you are given a single graph and you want to find the automorphism group of the graph, which is a finite group. So in practice, there are some quite good algorithms to do it. They use a combination of backtracking, some combinatorics, some group theory, and they are fast on most instances, even though you can find hard instances. And not only they allow you to compute isomorphisms and automorphisms, but they also allow you to have a canonical form for graphs up to isomorphism. So for graphs, a canonical form would be essentially an ordering on the vertices, such that when you take two graphs and you give them both the canonical ordering, then the edges are literally the same for this ordering. Okay? So as we saw before, having a canonical form is better than just being able to test isomorphism. So that's in practice, and there are several software that can do that very quickly. In theory, the situation is actually fairly good also, because we know that there exists a quasi-polynomial time algorithm to test isomorphism. So it's also almost in the polynomial time class. That's a recent result of Babai, and it's an algorithm that mostly uses group theory. So I will show you an example of an application of the isomorphism problem for graphs to another isomorphism problem. So the thing is, because graphs encode almost any type of information, there are many isomorphism problems that you can reduce to an isomorphism problem for graphs. So the example is the lattice isomorphism problem. So recall the problem, you're given two lattices and you want to find an isomorphism between them, meaning a linear map between the two that is, a bijection, but that preserves distances, okay, an isometry. And so how do you reduce it to the graph isomorphism problem? Well, first you need to construct some kind of finite set that characterizes isomorphisms. So we'll choose a bound such that the set of vectors up to that bound generate the lattice. So definitely isomorphisms will be completely determined by their values on this set. And you will create a graph that has this set as a vertex set, and you will encode the extra data that you want to preserve, namely the distances and even like the inner product from your Euclidean norm. And so you will put edges between, in fact, every pair of vertices, and even loops on each vertex to itself, with a weight that is just the inner product between the corresponding vectors. And you can show that lattice isomorphism reduces to graph isomorphism on this graph. So if the graphs are isomorphic, then well, in fact, the actual isomorphism between the graphs induces an isomorphism between the lattices. You get the linear map. So that allows you to reduce lattice isomorphism. But in addition to this, because you're also allowed to compute canonical forms for graphs, you can build on top of it a canonical form for lattices. So there's been recent work on this. So you need to work a bit more if you do this, because the canonical form on the graph doesn't immediately translate into a canonical form on the lattice. You have to work a bit more, but it's possible to do it. And that allows you to treat huge numbers of lattices. I mean, there are some contexts where you want to do duplicate and elimination, like I mentioned at the start, on lattices, and that's the best way to do it when you have these huge numbers. One thing I should say is that it's not, so we saw that lattice isomorphism, we only had quite slow algorithms for that, right? And on the other hand, for graph isomorphism, we have quasi-polynomial time in theory and relatively fast in practice. So the problem is in this reduction, the vertex set that you create is extremely large. So it's not a very efficient reduction, but still it's a useful one. Okay? So that's why you don't get as fast lattice isomorphism as graph isomorphism. Okay, one extra, not really algorithm, but a property on graphs that is useful to think about in algebraic context is the spectrum of a graph. So from a graph, so for now I will think of an undirected graph, you can create its adjacency matrix, which has coefficients, rows and columns corresponding to the vertices, and you put coefficients when you have an edge. So, okay, maybe something like this. We'll have a 4x4 matrix. You put ones on the diagonal, and it's here I'm taking undirected graph, so it's going to be symmetric. And so, okay, I have from 1 to 2 and 3, so and from 2 to 3, yes, and 3 to 4, whatever. Okay, that's my adjacency matrix. And if you look at what happens when you consider powers of this matrix, you realize that this counts exactly the number of paths of length k, or well, I guess I put one on diagonal, so path of length at most k, or k if you count, if you force to have loops here on all the vertices between I and j, and therefore this linear algebra object detects a number of paths. So whether things, in particular, it detects whether things are connected or not. And so because you look at these iterates, the spectrum of this symmetric matrix will tell you something about how fast you converge, for instance, to eigenvectors. Okay? And a way to interpret this is, for instance, is that this spectrum will determine how fast random walks on the graph, where you choose one of the out edges at random, will give you a distribution on the vertices that is equidistributed. So maybe the simplest setting for this is when you have graphs that are regular, meaning they have the same, each vertex has the same number of outer vertices. And if you're in this setting, well, let's say that you divide the adjacency matrix by this number of outgoing edges, and then you will have vectors with eigenvalue 1, which correspond to the connected components. So these vectors with just ones will correspond to a distribution of points that is completely equidistributed on a single connected component. And the iterates of the matrix, so you'll have smaller eigenvalues that correspond to how fast you converge to these distributions equidistributed on a connected component. So you can, well, that's maybe an instance of going the other way from graph theory to linear algebra, in a sense. And so if you can analyze the spectrum of these matrices, for which you could have other special tools, then you understand if things are connected and how fast they equidistribute. Okay, we'll see an instance of this in a certain sense a bit later. So the second part I want to talk about is L functions. So I will start with a few motivating examples of L functions. So, okay, in the second lecture, I talked just a little bit about the Riemann hypothesis for and the zeta function. Here, I will give a bit more details on the various L functions that you can have and what the Riemann hypothesis means for them. Okay, so first we take a number field and we consider the following product. Take the product over all prime ideals of f of 1 minus norm of p to the minus s to the minus 1. So this type of product is what is called an Euler product. It's a product over primes of some sort, I mean prime numbers or prime ideals. In fact, you can expand this product and rewrite this as a sum, and what will appear are the norms of all the integral ideals of your field. That's essentially a reformulation of the prime decomposition of ideals in ZF. Okay, so you can form this product, and the theorem is that it extends to a meromorphic function with, in fact, a single pole at s equals 1, and such that if you add these extra factors, so what are the factors that you add? Some functions gamma r of s to the number of real embeddings of your field, and gamma c of s to the number of pairs of complex embeddings of f, where, these are the, so this is the classical gamma function. Gamma r is just pi to the minus s over 2, gamma s over 2, it's just a variant of the gamma function. And gamma c is just a product of two gamma r's, and this is a typo, it should be a capital gamma. The main point being, if you add these gamma factors and some integer here, absolute value of the discriminant to the s over 2, this completed function satisfies the functional equation, lambda s equals lambda of 1 minus s. Okay, so maybe you will ask, what is the point of doing this construction? Well, the point is you can use the analytic properties of this function to count, for instance, the number of prime ideals up to a certain bound. Okay, I'll say a bit more about it later. Okay, first example. Let's do a second example. So now we take n to be an integer, and we consider a character from the group of invertible elements modulo n to c star, multiplicative character. And you can form, again, a type of Euler product here. The product is over primes that don't divide n, and you put the values of the characters here. Oh, and there's again a typo, this should be a minus 1. And the theorem, again, is that it extends to holomorphic function. I guess I should have said if, well, should include the if chi is primitive and not trivial. So primitive meaning that it doesn't come from a smaller n. Such characters may come from a smaller n. In this case, the L function will have slightly less good properties. It satisfies a functional equation of a type that looks a lot like the one we just saw. So there's an integer to the power s over 2. There's a gamma factor with a certain shift. And our L function, it satisfies the functional equation, again, between s and minus 1 minus s. But note here, it might not be 1 here. Maybe the functional equation could be lambda s is minus lambda 1 minus s. And the shift depends on the character also. So again, you may ask, well, what is the point of doing this construction? Well, the point is that, again, by analyzing the analytic properties of this function, you can prove the fact that there are infinitely many primes in any arithmetic progression. Like you choose any element of Z mod Zn star, then you'll have infinitely many primes that are congruent to that modulo n. Okay, so second example. Let's see a third example. So now we take E to be an elliptic curve over Q of conductor n. If you don't know what the conductor is, it doesn't really matter. It's an integer that is attached to E. And you can create again an L function. Well, here I've hidden a few of the factors because they're a bit more complicated, but you have a finite number of bad factors, the ones for P dividing n, that are slightly more complicated to determine. And that's actually a general fact that there's a finite number of factors that are harder to determine than the other ones. And the ones for P not dividing n are just given by 1 minus AP, P to the minus S, plus P to the 1 minus 2S, where AP, oh, I couldn't write it here. So where the number of points of E over FP is just P plus 1 minus AP. This is the definition. So this is built, so this Euler product is built from the number of points of E modulo P. And again, we have extension to a holomorphic function on C and a functional equation of the same type, integer to the S over 2, again a gamma factor, and the functional equation. So here what you should notice is that the functional equation is in terms of S between S and 2 minus S. But that's not actually a real difference because you can always make a shift of your variable that will reduce everything to lambda S becomes lambda of 1 minus S. But it's sometimes more convenient to normalize things in a different way. Here, the advantage of keeping this normalization is that the coefficients that appear here are integers. If you normalized it to have S and 1 minus S, you would need to introduce a square root of P at every factor. Okay, so this is called the arithmetic normalization, and you can make the analytic normalization by doing a shift. Okay, so another example to see again, a bit more what the variety of things you can see. So you can start with F, a real quadratic field, and I will assume narrow class number 1, meaning not just class number 1. So class number 1 would be every ideal is generated, well, is principal is generated by some element of the field. Narrow class number 1 means every ideal is generated by an element that is totally positive, that is positive in every real embedding of F. Okay, and I will call U the fundamental unit of the field, so meaning a generator of the group of units of ZF modulo plus or minus 1. And from this data, you can form the following Hecke L function. As the previous ones, it's a product over primes of 1 minus this quantity, which is something that depends on P. So you take a totally positive generator of P, and you take the log of that divided by the log of the fundamental unit. And again, times norm of P to the minus S inverse. And maybe what you should notice, and that was also true for the other example, is that the quantity that appears here has absolute value 1. Okay. Oh, and I should, no, okay, yeah, no, this is correct. And you have, again, a functional equation of the same type as before with an integer to the S over 2, gamma R of gamma shift, and I see now that I made a mistake, there should be an I here. So the point is, all the examples we had before, the shift here was by a real number, and in fact just by an integer. Like this is an example where you have an imaginary shift. And there should be an imaginary shift in one direction and the other. So, okay, my point is that you have this shift, which is not an integer in general. This is most likely a transcendental number, and it's imaginary. It's not just a real shift. And the functional equation is also generalizing the previous ones, but slightly more complicated. So S is related to 1 minus S, but really to 1 minus S bar and the function in which you take again the complex conjugate. And you have W here that doesn't need to be plus or minus 1. It's just some complex number of absolute value 1. Now, these complex conjugates, that's actually almost the same as just taking S to 1 minus S, except that you also need to take the complex conjugate of these coefficients that appear in addition. But it's a very minor variation on the one we did before, related to the fact that the coefficients here are not all real, whereas in the previous examples, all the coefficients were real. Okay, so from these examples, I want to give a general definition of what we call an L function. So an L function of degree d, an integer and conductor n, that's a meromorphic function on C with finitely many poles that is defined for, well, okay, all the Euler products, actually I didn't say it, but all the Euler products that we had before, they converge only for a real part of S sufficiently large. And the whole meromorphic function is only an analytic continuation of that. So defined for a real part of S large enough by an Euler product of a form, so this form will generalize all the ones that we have seen, product of some polynomial evaluated at prime to the minus S, where all these polynomials have degree at most d, and they're 1 at 0. This is just to make them of the form 1 plus p to the minus S plus etc. that ensures convergence. So, and the degree should be exactly d, and with all roots of the polynomial of modulus 1 for p that doesn't divide n. So for the good primes, you should have exactly degree d and all roots of absolute value n. Again, if you look at the previous examples, that's a generalization. And satisfying a functional equation like before, so you complete the L function by your conductor to the S over 2 times the product of gamma factors. Okay, and there's L of S missing here. Satisfying a functional equation like the most general one we've seen, so relating S to 1 minus S with complex conjugates because maybe the coefficients here are not real, and absolute value of W is 1. And so each of these type of L functions will have analytic properties that tell you something about the distribution of primes in relation to the object from which you constructed the function. So in the earlier examples, for the Dedekind zeta function, it tells you something about the distribution of prime ideals in the field. For the Dirichlet L functions, it tells you something about the distribution of primes modulo n, etc. Okay, so let's see a few more sources of L function in a little bit less details. So one other source of L functions are so-called modular forms. So let me just give you tiny bits of details on what these are. So you consider the Poincaré half plane, which is the set of complex numbers with a positive imaginary part, and you have an action of SL2Z on this by ABCD acting on Z, AZ plus B over CZ plus D. And a modular form is a function from H to C, which is, holomorphic. And, okay, there's a few properties, but the main one is that f of gamma z should be related to f of z for all gamma in SL2Z. There's a few more properties. So this is the main. This is what justifies the word modular, and then you ask for a few more properties, and then to get an actual L function in the sense that I defined before, you need an extra property given by the action of certain operators indexed by primes. So we usually call them TP, and we want TPF equals APF. So I'm not giving what the operators are here, but they are given by fairly explicit sums related to the values of f. And we are asking that f is an eigenvalue of these operators. So this is just a complex number. And you can form the L function by putting together these coefficients into the Euler factor. And there is an even more general construction that follows the same general shape, but more complicated. So you have functions on certain spaces satisfying a certain transformation law under a certain group, and you have more Hecke operators under which it needs to be an eigenform, and you can put all of this into an L function. And the main point of this source of L function is that this is basically the only way that we know how to prove the analytic properties that we want for L functions. Okay, so that's one source. Then you have curves and varieties. So so that's a generalization of the elliptic curve case that we talked about. So you take a curve or an algebraic variety defined over Q or a number field, and you put together the number of points of X modulo P. That allows you to construct an Euler factor of a polynomial that gives you an Euler factor as before. You have some gamma factors that come from the analytic properties of X when you see it as a curve over C. And the integer n that appears, the conductor comes from the bad reduction of X, like the primes at which reduction modulo P is not well behaved. And again, you can put all of these together into an L function. And another source, which is actually related to the previous one, is what are called Galois representations. So remember that we can attach a Galois group to certain extensions of number fields. In fact, it could be finite or infinite, but well, it's enough to think about finite for now. So a Galois representation is just a morphism of groups from a Galois group to some GLD of E, where E is some field of coefficients. And from certain types of Galois representations, you can form L functions in the following way. You get the Euler product from the characteristic polynomial of the Frobenius elements. So you have Frobenius elements corresponding to every prime in these Galois groups. You can take their image on the row, that's a matrix, and you can look at its characteristic polynomial, and that gives you the Euler factor at the corresponding prime. The gamma factors are essentially determined by the eigenvalues of complex conjugation. So you have elements that are a bit like the Frobenius, but they correspond to real and complex places. And the conductor essentially comes from the ramification properties of the extension. So you have also a similar type of construction like this. Okay, I think it's a good time maybe to take a break. Mm-hmm. Okay, so to give some idea of the importance of these L functions in number theory, I want to mention a few conjectures about L functions. that are, well, mostly not unresolved. So the first one is the generalized Riemann hypothesis. So I actually gave you the formulation in the second lecture for the Riemann zeta function, but more generally what we believe is that if you have a zero of an L function, then its real part has to be at most 1/2. Actually, just this is the conjecture if you have a functional equation relating s to 1 minus s. For instance, for elliptic curve, you have to do the translation to write it like this. So this is widely open, and what we actually know is a very, very small region in which we know that there can't be any zeros. So let me draw a picture. So this is 0. So in general, the region of convergence will be a plane that starts here at 1. 1/2 is here, and this is, so this is where we think the zeros are, and actually, I mean, there are always zeros there, but they're not very interesting. And so yeah, so we believe that all the zeros are on this vertical line, and what we can actually prove is that there can't be any zeros in some very thin region that basically looks like this. Something that gets really close to the one line. I mean, it does a little bump here, but then it gets really close to the one line here. And we know, so what we know is that there cannot be zeros there. But for all we know, there could be zeros very close to here. Okay? And also, even that's not even quite true, because we're not even able to rule out the fact that there could be one exactly very, very close to one in there, but just one. So that's the best we know. Okay, so that's the first important conjecture. We'll talk a little bit about applications of this, why this is actually useful. Another conjecture is the so-called Lindelöf hypothesis. This is actually a consequence of the Riemann hypothesis. So in a sense, you could say, well, we don't care about that particular conjecture because the other one is stronger. But the point of this one is that we can prove something about it that is non-trivial. So the conjecture says that if you look at the values of your L function on this line here, so notice this line is the line of symmetry of the functional equation. That's why it's important. So if you look at the values of the function on this line, it has to be very small, bounded by a constant, maybe depending on some epsilon of the conductor to the epsilon times 1 plus the height to the epsilon. Okay? So it has to be very small along this line. And what is known automatically, like somewhat easily, it basically follows just from the functional equation, is that this is true for epsilon, which is 1/4. If you put 1/4 here, this is true, but we would like it to be true for all epsilon, even smaller. And sometimes we can prove 1/4 minus a small amount. And that's called, when we can prove something like this, that's what people call subconvexity, proving subconvexity for an L function. So if you see that word, that's what it means. Okay, so that's the second difficult conjecture. There's a set of conjectures, in fact, not just a single conjecture, about the values of the function at certain very special points. So there's a whole family of such conjectures, and for instance, they are related to the order of vanishing at certain points, or the actual value of the function there. And they have a certain interpretation in terms of other objects that are not directly related. So one example of such a conjecture is the Birch and Swinnerton-Dyer conjecture. about L functions of elliptic curves. And in this case, the conjecture is that the order of vanishing at S equals 1 should be equal to the rank of E of Q. So recall that E of Q is a finitely generated group, so it has a torsion part and a finite rank part, Z to some rank, and the rank should be the same as the order of vanishing. And the conjecture is actually much more precise. So, so you have this L E of S. So at S equals 1, it starts S minus 1 up to some order of vanishing, and then there is a first term, like alpha. And so not only do we believe that this R is equal to the rank of the curve, but we also have an expression for this number in terms of invariance attached to E. And we believe that this is true. And what is known about these? Well, there's a number of special cases that are known. For BSD specifically, elliptic curves, this is known essentially for rank 1 or 0, which is already quite difficult. There's one special case that's actually easier, that was known much earlier, which is called the analytic class number formula. So this is for the Dedekind zeta function. So the Dedekind zeta function, like the Riemann zeta function, it has a pole at L equals 1 of order 1. So there's a pole, and then there's a main, there's a coefficient of the pole, which is the residue at S equals 1. And this has an expression in terms of the invariance of the field. So actually, I'm not going to give the exact formula since I will make a mistake, but there's basically a function of the discriminant of the field, the number of roots of unity, and most importantly, the class number times the regulator. And this one is known. This is like the easy version of this type of conjectures. Okay, one more conjecture. Actually, something I didn't mention earlier is that in many of the constructions that we saw of L functions, we don't actually know that there is meromorphic continuation and functional equation. And the only way we know how to prove it is by showing special cases of that conjecture, which is that all L functions in the sense that I described should actually come from automorphic forms. They should come from one special construction. So in particular, you can have L functions that are constructed in a completely different way, and you equate them with an L function of an automorphic form. So there are many special cases that are known, and I guess probably the most famous cases of this are the ones obtained from Wild's method. And when I said earlier that we know that the L functions of elliptic curves are actual L functions, this is because of that theorem saying that the L function of an elliptic curve actually equals that of a modular form, and for a modular form we know the analytic properties, and that's how we know that the L function of an elliptic curve actually has these analytic properties. And actually, if we didn't, it wouldn't even make sense to ask about this BSD conjecture, because it's asking for something at a point where the Euler product doesn't converge. So if you don't show analytic continuation, the conjecture doesn't even make sense. Okay, so let me talk a little bit about algorithmic parts of L functions. So there are two sides of this. There is the question of how do you compute with L functions? Like if you see L functions as objects of interest, you want to be able to compute some things about them. And there's also what L functions actually give you that you can use in other algorithms. That's the other side of the story. So the first one is the computation of the coefficient of your L function, of the Euler factors. So one of the cases where it's the most interesting is that of varieties. And so, okay, for varieties, X, so the computation of the good Euler factors, the one at the primes where reduction mod P behaves well, then it really essentially reduces to thinking of, of a variety over Fp or finite fields. And the question is, can we count the number of points over Fp? And in fact, you need to know it over various extensions of Fp. And so we have algorithms in a certain number of cases that are efficient. For instance, for elliptic curves, we have a polynomial time algorithm, let's say. And for general varieties, we don't quite have a polynomial time algorithm, but we have something which is polynomial in terms of various parameters, but there is an O of P, or even in some good cases, O square root P factor. So that's not quite polynomial if you have something like this. That's actually exponential with respect to the size of the finite field. On the other hand, when you want to do computation with L functions, you will only care about computing the Euler factor for small p's. If you want the beginning of the expansion of the function. So P will be relatively small, so this is not actually that bad because you want to count. So all, let's say, psi of x of Fp or n extensions for P up to some bound. And so if you have something where the complexity is something like this, for instance, and you sum all of it, then you will have maybe b to the 3/2. And so, yes, for a single p, this is not polynomial time because you could imagine that p is very large. But on average, for all p up to b, then this is actually polynomial time. Okay? But in fact, we can do even better. There is a fairly general algorithm by Harvey, which does all of these count up to b, but in quasi-linear time. So soft O of b. And so that's exactly what you want. You want to be able to count all up to some bound in, well, quasi-linear time. It doesn't matter that it's not enough for a single p if p is very large. This algorithm is more of a theoretical type. Like it's not implemented in the most general case of an arbitrary variety, but there are many interesting cases where you can actually reach that performance. For instance, I think hyperelliptic curves, that's, I don't know if it's done in arbitrary genus, but something like this, they know how to do efficiently. Okay, so that's for the computation of the good Euler factors. Then you would like to be able to evaluate your L function at various points. For instance, when you want to test these conjectures about special values, or if you evaluate the function, then you'll be able to compute the zeros up to a certain height and check the Riemann hypothesis, things like this. And so evaluation essentially uses something called the approximate functional equation. So the approximate functional equation is an expression for the value of the L function. You obtain it from the usual functional equation by some complex analysis arguments, and it expresses L of S as a sum, as a rapidly converging sum where to reach a given precision, you essentially have to sum only terms up to b, which is essentially square root of n being the conductor that appeared in the functional equation. And it's an expression that converges even when the Euler product doesn't. So that's enough to evaluate at other points, the ones that are in the critical strip or etc. And so essentially, so to apply this, you'll have to evaluate the good factors up to b, which is square root n, and you will need the bad Euler factors because you need all the factors to be able to actually evaluate the function. And so the bad Euler factors, that's something that is in general not easy to get. I mean, there's a number of special cases where we know how to do it. But one thing that you can do, if you have a lot of good Euler factors and you're missing just a few Euler factors, you can use the functional equation or the approximate functional equation as you evaluate them at a certain number of points, and you use these as equations on the coefficients that you are missing. You see the coefficients that are missing as variables, and you write the equations that these functional equations give you. That gives you a system. Depending on how you do it, it's either linear or non-linear, but you can solve it and get the missing bad Euler factors this way. So even if you don't have a nice algebraic, say, way of obtaining these bad Euler factors, you can get them from the functional equation. Okay, so these are the main algorithmic problems that you can think about on L functions. And now I want to finish on some actual applications of GRH, which can in turn be used in algorithmic context. So, eraser. In general, I'm calling these a strong prime number theorem. So what is the prime number theorem first? So this is just the theorem saying that the count of primes up to x is essentially of order x over log x. And this is obtained by looking at the analytic properties of the zeta function, the Riemann zeta function. Theorem. And there's a version of this that you obtain from L functions. And if you assume the Riemann hypothesis, you get a very strong version of this in the sense that the remainder term will be very small. So how does it work? Well, how does this relate to L functions? Well, the way it works is that if you look at zeta expressed as a product like this, so this is a product, but if you want to extract information about the primes, it's better to have a sum over primes, because basically then it will be essentially like a generating function. So to go from a product to a sum, well, you want to take a log. In fact, it's slightly nicer analytically to take not the log, but the logarithmic derivative, because the log derivative, it preserves meromorphic functions. The log derivative of a meromorphic function is meromorphic. You don't get nasty singularities. And so if you take the logarithmic derivative, then you will get a sum over primes, and in fact over powers of primes of, well, if you do the calculation of log of p, I guess that will be a minus probably. No, well, maybe let's put it here. P to the minus ks. Okay, so this is essentially a sum over primes. And then how do you obtain the counts that you want? Well, so let's write again our diagram with the 0 and 1 here, and 1/2 there. So from this expression, which converges for real part of S large enough, you can rewrite something closely related to this prime count in terms of a certain integral over a path like this of this logarithmic derivative. And now, if you shift the path of integration by using complex analysis, you can shift the path of integration and push it to the left, like maybe even, let's say, to here. The effect of pushing it to the left will be that the terms get smaller, because the main factor is something like t to the s. So the more to the left it is, the smaller this is going to be. Sorry, x to the s, where x is my bound on the count here. But what happens when you push like this to the left is that this function has poles, and you pick up a term every time you pass a pole. So there's a pole at s equals 1, and then depending on whether you assume GRH or not, the poles are somewhere. And if you assume GRH, the poles are here. And so you pick up, when you pass this, you pick up a term in x. That's the term you would like to have. And you go here, you pick up terms that are like x to the rho over rho, where rho is the 0. But if the real part is small, this is actually of order essentially square root x. So this is what gives you small error terms. And if you do the calculation, you realize that the error terms are also very small, not just in terms of x, but also in terms of n, the analytic conductor. And so putting these together, there are several applications. One of them is the generation of class groups by small primes that I mentioned before. And essentially, it's an application of the equidistribution properties I mentioned on graphs. So what happens is you can think of the class group as being a graph where you have a vertex for each element, for each ideal class. And you choose a set of small primes and you put edges when you can connect two ideal classes by multiplying by a prime. And the spectrum of that graph is related to the type of things you get here for certain L functions. And so if you use the good bounds that you get from GRH, then you can prove that in this graph, random walks mix quickly. And also, as the most important one for this is that the graph is actually connected. The graph being connected being the same as saying that the group is generated by the set of primes. So that's one part that was sort of a black box that we had in our algorithms to compute class groups. And the second one was that we wanted to be able to compute class number times regulator at low precision to have a termination criterion for our index calculus algorithm for class groups. And that also comes from the Riemann hypothesis. You can do this fast evaluation at low precision. Again, because of the good analytic properties, you'll be able to write the value as a very short sum, and so you can evaluate it quickly. Okay, these are the last things I wanted to say about L functions. So this is the end of the course. Thank you, and well, I'll answer your questions. Thank you.